Okay, ladies and gentlemen, this is the problem under consideration. And the first thing we want to do, part A, is to draw a ray diagram. And I like to use the solve method, which is to draw a sketch, which is what this ray diagram does, and then organize our knowns and unknowns. And I like to do that, I personally like to do that right on the sketch. So I'm labeling. The focal length of the objective is 24 millimeters. The focal length of the eyepiece, and I'll put that up here. I'll put it up here. I want to get it out of the way so it's not going to block any of the ray diagram. So that's the focal length of the eyepiece. Distance between lenses. Now, Halliday and Resnick uses S for the letter of the distance between lenses. Other authors use the letter L. So in case somebody is reading another book, I'll do this. And that is given as 320 millimeters. And finally, the near point distance. Where we want the image to eventually end up is actually over here somewhere. But for the sake of simplifying the drawing, I'm going to put the final image right here. And at the same time I'm drawing it, I'm going to draw my line through the center of the eyepiece, and this is the near point distance. And Halliday and Resnick uses the number 25 centimeters. It depends on the person. Different people will view things in focus when this is different lengths. Remember that near point distance has to do with you're looking at it with your eyeball. And different people focus the microscope at different distances. 25 centimeters is common, which Halliday and Resnick uses. For this problem use 400 millimeters. And I'm going to put the distance of the image. This distance here between the lens and this is the image formed by the objective lens. And it is formed very nearly at the focal length of the eyepiece. There we go. Now, the first image. So this would be the image, and draw a line straight through. All lines going through the through the center of the lens are deflected. Are not deflected. Excuse me. Are not deflected. A line going through parallel lines parallel to the optic axis will intersect at the focal length of the objective. So there's the line that's parallel to the optic axis, and there's the line that's going through the center of the lens, and where the two intersect is where the first image forms. So this is the distance of the object. This is the distance between the objective lens and the image. We'll call this d sub I. This equals the image from the first lens becomes the object for the second. D2O, the object for the second lens being the eyepiece. And then finally, this is DIO. And that'll equal 400 millimeters, by the way. So now we can start getting our magnifications. We see that the image from the objective lens is going to form at L minus F sub E. L minus the focal length of the eyepiece. I just drew those a while back. I'm going to erase them now. Distance of the object is going to be equal to the focal length of the objective lens. D2 of the object is going to be the focal length of the eyepiece. And D and I don't know why I should have said D2I. That's the convention I'm using. This is the second image. This is the first image. This is the second image. The image formed by the eyepiece. D2I is going to equal N, 400 millimeters. So we can get our magnification formulas. Magnification total is going to equal to, the first magnification is going to be the image over the object. L minus focal length of the eyepiece, the length of the tube minus focal length of the eyepiece divided by the focal length of the objective. Remember, when you're finding multiplications, you just multiply the two, the magnification due to the first lens times the magnification due to the second. Well, the magnification due to the second is going to be N over F sub E. Now I'm going to pause. We've got our formula. What is the magnification? We've got our formula. This is part A of the problem. This is part B of the problem. Question B. I'm going to pause the recording for just a moment to do the calculations. Rounded to 3 sig figs, I get an answer of 317 times magnification. Part C. For ordinary crown glass, you have the objective, it looks like this. One side flat, the other side curved. And you want to know what's the radius of curvature of this curved side. Well, the formula is actually pretty easy. 1 over F equals N, little n, index of refraction N minus 1, not big N, not this N, the little n. Times 1. It's 1 over the radius of curvature of one side minus 1 over the radius of curvature of the other side. Since one side is flat, that radius of curvature is infinity, so we just have to write this. We know the focal length is 24. It is the focal length of the objective, and we just solve for R. Radius of curvature is going to equal to N minus 1, the index of refraction minus 1, times, it's going to be times the focal length. There we go. I just cross multiply. That's all there is to it. And another pause to do some calculations. I'm back, and I got 12 millimeters. Part C. Part D. Reflecting lenses. You can use a reflecting lens. It's a catadioptric. There's lots of different designs. They basically have the main objective lens here, and then they have a folding mirror, and it sends the light rays back this way. The main idea is you can make an objective lens for a microscope using a mirror. And the basic question is, what is the focal length of the mirror compared to the radius of curvature? Well, the focal length is half the radius of curvature. Focal length of the objective is R over 2. So we get R equals 2F objective, and I can calculate that in my head. That's 48 millimeters. Okay, so that gives us, okay, we're done with this problem. End the recording.